Hello again. Sorry that it's been a month or so. Been working on some other stuff like a new Psych and Soch deck, as well as a textbook that I'll be releasing for free sometime later this year, the year of our Lord 2025. But while I'm in the middle of kind of this series on metabolism videos, I did want to release a video really quickly that would basically just make understanding all of this information that you need to know for metabolism on the MCAT easier to understand. I understand there's so much stuff that you need to know, but I'm hoping that a video like this can help you compartmentalize that information and make everything much easier to understand. I'm basically going to help you connect all of these processes to each other rather than you just having a giant bullet pointed list of stuff that you need to know for metabolism on the MCAT. Of course, as always, you can click the link in the description of this video where I will have basically some notes that are going to support this video. Obviously, this is going to be much more of like a summary video that I'll have these just listed out with a few other notes listed underneath them. But especially for a video like this, I definitely recommend just sitting back and listening and then only writing down anything that feels significant to you, something that you didn't necessarily understand before. So again, if you're basically looking to make metabolism easier, this is the way that I recommend doing it. There's technically two ways, but semantics, you'll see what I mean here in a second. So the first way is to start off with the metabolic states, right? So there's going to be three different metabolic states. The first one is called the fed or absorptive or the postprandial state. This is literally when, like I mentioned, your tummy is full. Whatever your favorite restaurant is, whether it's Cane's, Taco Bell, Wendy's 4 for 4 that I don't think exists anymore, whatever it is, you've just sat down, you've just eaten that, and it's in your stomach. And so this is what's happening to that glucose and all of that food that you are currently digesting. So first, in this fed metabolic state, as we keep digesting that food, our blood glucose levels are going to be pretty high, but our cellular ATP levels are going to be pretty low. That's why we eat, because our ATP levels are low and we need to provide some sort of energy that will allow us to produce that ATP. So we're going to solve the first problem, which is the ATP shortage. So what we're going to do is we're going to use that blood glucose to make ATP. The main process that we're using to do that is called aerobic respiration. Aerobic respiration is everything that happens from glycolysis all the way through the Krebs cycle, where we're basically producing that 32 ATP per glucose, roughly. In this phase, since there's a lot of glucose around as well, we can keep running other side processes like the pentose phosphate pathway. So that's also going to be active during the fed state at various times. So now that we've made ATP, there's going to be a point where we actually have enough ATP. Our cellular ATP levels are high, but we still have glucose left over in the blood. So we don't need to be turning that glucose into ATP anymore. So we don't need to be doing aerobic respiration. So we'll just turn around and store that excess glucose. The process is that we're going to be doing that to store glucose as glycogen. That's a process called glycogenesis. We call this short-term energy because glycogen pretty much only exists within a 24-hour period in our body. It doesn't exist for much longer than that. And then we're also going to have some excess acetyl CoA laying around the body as well that we can turn into fatty acids. And those fatty acids are going to serve as our long-term storage. So basically, in this fed metabolic state, we're going to be taking all of that glucose out of the blood, and we're first going to use it to make ATP. If we have enough ATP, then we're going to store it. All of that is happening in this fed metabolic state, and all of these processes are promoted by insulin, which is why everything's in blue. So as we come out of the fed metabolic state, after a few hours roughly, there's not like a specific time that you need to know, we're going to enter what's called short-term fasting. This is also called the post-absorptive state, where basically your tummy's empty and it's been empty for a while, so ATP levels are starting to drop. Right? We've already stored all of that excess glucose as glycogen, but now our ATP levels are starting to come down again. So at this point, our blood glucose levels are low because we've either used it or stored it as glycogen, and our cellular ATP levels are dropping. So all we need to do is just make more glucose. And the two ways that we're going to do that, mainly done by the liver, there are a few other exceptions to this that we're not going to cover right now, but the liver is going to be starting off with gluconeogenesis, which we're going to be taking pyruvate and turning it into glucose. And it can also do glycogenolysis, the breakdown, the lysis of glycogen. The liver is doing both of these processes to produce glucose that it can then put into the blood and ship around to the rest of the body where that glucose will be used, places like the brain, of course. So again, blood glucose levels are low, our cells need ATP, so the liver is going to produce glucose that can be shipped around the body to solve both of those problems. So both of these processes that are occurring in this short-term fasted state are both going to be promoted by glucagon. Blood glucose levels are low. Glucagon is going to respond to get the liver to produce more glucose for the blood. And then that glucose will get shipped around the body to wherever it needs to go. But from here, let's just say that you still haven't eaten another meal. So your body is starting to really dip into its reserves at this point. There's going to become a point where your stomach is still empty. I would even say like super empty. And at this point, you have no glycogen or glucose left. So because of this, we kind of have to go a different direction than glucose. So just to look at what's going on at the first point of this state, our blood glucose and glycogen levels are both low, and our cellular ATP levels are also low as well. So we need to put something into the blood that the cells can use to produce ATP, but it can't be glucose since we're out of glucose and we're out of glycogen. So at this point, mainly the liver, but again, there are a few other tissues, is going to be dipping into that long-term store of energy, those fatty acids, to produce energy. This is the first thing that we do once we enter the long-term fasted state. Whenever we break down fatty acids, that's a process called a beta oxidation, and that produces a molecule called acetyl-CoA. You probably know that because of the Krebs cycle, right? So this acetyl-CoA can essentially be sent around the body for our tissues and cells to take up and just put it straight through the Krebs cycle. But there is a slight problem with this. Coenzyme A is huge and it cannot travel through the blood. So because of that, we kind of have to turn this acetyl-CoA into something that can travel through the blood, just as like a temporary version of acetyl-CoA that's water soluble and can travel through the blood. And then when it gets to its destination, we just turn it straight back into acetyl-CoA for the Krebs cycle, right? So for example, the liver will produce some acetyl-CoA through beta oxidation. That acetyl-CoA, before getting sent into the blood, will undergo a process called ketogenesis, where we're turning that acetyl-CoA into a ketone body. The ketone bodies can freely travel through the blood. And then once they get to their destination, let's say one of those little tiny brain cells that's active right now and probably really tired and wanting Taco Bell or something like that, that wants me to just shut up. One of those brain cells is going to pick up that ketone body and then turn it back into acetyl-CoA so that it has a molecule it can run through the Krebs cycle. And the Krebs cycle is really good at producing ATP. It can produce 10 ATP per acetyl-CoA. Obviously, I have videos or other notes and stuff like that to explain all of these processes in full. I don't have any videos out about the fasted states, but those are coming sometime this month. But long story short, if you do have questions about each of these individual processes, I highly recommend going and watching any of my other videos. So basically, at the start of this long-term fasted state, we are using acetyl-CoA through fatty acids to produce ATP around the body. But there becomes a point that we might run out of fatty acids. This is like if you've been starving for like a week now at this point. I usually kind of explain this to people that if you've seen the movie Castaway, like we're now at the point that like you haven't eaten a meal in like a week and your best friend is a volleyball that you've named Wilson. So this is a pretty dire circumstance now at this point, where when we run out of fats, we turn to breaking down proteins. This is a worst case scenario. We do not want to be breaking down proteins in our body because obviously proteins have a lot of really important and vital functions to how we exist. So this is a last resort for our body to be able to produce ATP, especially for the brain. The brain's really selfish and wants to always be able to produce ATP for itself. Freaking jerk. So there's going to be some amino acids that can be turned into acetyl-CoA. We call these ketogenic amino acids. And then there's other amino acids that can be turned into some form of glycolytic intermediate, whether it's F6P, G3P, anything that you see in glycolysis. It doesn't really matter. We call all of these that are going through glucose metabolism, we call them glucogenic amino acids. Again, we won't fully dive into that right now, but basically protein catabolism is our last resort way of eventually producing ATP by breaking down amino acids into acetyl-CoA or something in glycolysis. And finally, if you're catching on to my color coordinated system, you'll note that every single process that occurs in the long-term fasted state is also promoted by glucagon. The other thing that I'll mention really quickly is you'll notice that I also put in parentheses that epinephrine and cortisol can also stimulate all of these processes. Basically, they all can stimulate the exact same processes, but they do so for a different reason. Glucagon is basically just the normal, everyday fluctuation of metabolic processes. Epinephrine is the fight or flight response, which is kind of like an extreme circumstance. And cortisol is for stress, where something's going on in the body and we need to kind of liberate some glucose and stuff like that to make sure that we have energy to figure out what's going on and how to fix it. Long story short, all three of those enzymes functionally do the same thing, just for different reasons. So if something's promoted by glucagon, we can also promote it with epinephrine and cortisol. Insulin is on its own up there. So this is the first way that I'm kind of recommending to start organizing the information about metabolism. Basically, if you can start off with what's happening when you eat a meal and go all the way until you starve to death, essentially, for lack of a better way of putting it, you're going to have a pretty good idea of why each of these processes is happening and what conditions will promote it. In the fed state, we're running a whole bunch of stuff that's using glucose or storing it. In the short-term fasted state, we're basically going to start dipping into that glucose storage. And then in the long-term fasted state, we're going to dip into our long-term storage. This is the first way that I'm going to kind of reorganize the information in your brain rather than just knowing here's what glycolysis is and here's what the PDC is. So simply put, in the fed state, there's going to be lots of glucose in your blood from your meal, and our cells need ATP. So at first, insulin is going to be released to help us turn that glucose into ATP. The main process that we're doing that is aerobic respiration. Or if we have glucose left over, we can store it as glycogen in a process called glycogenesis. We have a very similar process for acetyl-CoA that we turn it into fatty acids. That's called fatty acid synthesis. Very lazily and thankfully so named. Then in short-term fasting, now it's been a few hours since we've eaten a meal, our glucose levels are starting to fall and are getting pretty low, and our cells are starting to need ATP again. All of that ATP they produced at the start of the fed state is starting to run out. So then glucagon is going to be released, and this is going to tell the liver to produce more glucose, mainly through gluconeogenesis and glycogenolysis. Gluconeogenesis means the new generation of glucose, neogenesis, gluco. And glycogenolysis is the lysis of glycogen, if that helps with the naming. Then when we run out of glycogen and glucose, we enter long-term fasting, where now we haven't eaten in a very long time. We don't have any glucose. We don't have any glycogen. We only really have fatty acids left. So glucagon and those other two hormones that we talked about earlier is going to tell the liver to break up those fatty acids in that beta oxidation process, which is going to liberate that acetyl-CoA to the rest of the body. And remember, we need to turn that acetyl-CoA into ketone bodies so that they can travel through the blood pretty easily. And then finally, as a last resort, if we don't have any more fat, we're stuck with eating ourselves, basically. You're going to start breaking down your own proteins. So looking at the metabolic states should at least make it easier to connect each process to each other and see why glucagon is promoting all of these exact same processes. The other way that we can organize this information is by looking at the hormones. So we're going to start off by throwing glucose into the center of the page, which I technically know that that's not centered. So my apologies to those of you with symmetrical OCD out there. That's my bad. I promise. I just needed to make more room for stuff on the right than I did the left. So my bad. My apologies. Just don't yell at me, please. Okay. So we're starting off with glucose. And remember, like we started off with the fed state, basically we're going to be using this glucose to produce ATP through aerobic respiration. And if we don't really need any more ATP, we can start storing that glucose. So just to show you what that looks like, this glucose in aerobic respiration is first turned into pyruvate through glycolysis. This pyruvate is then shuttled into the mitochondria, where it's sent through the pyruvate dehydrogenase complex and turned into acetyl-CoA. Then this acetyl-CoA is sent through the Krebs cycle, where we produce a whole bunch of electron carriers, which can go through the electron transport chain and ATP synthase to produce ATP. Whole bunch of steps. I know I breezed over them, but basically this is how we turn glucose into ATP through all of these steps in aerobic respiration. So I want to note that going from glucose to acetyl-CoA, we are breaking down a molecule and we're using that energy from breaking down that molecule and storing it in ATP. We can also call these processes catabolic, or catabolism, meaning that we're breaking down molecules which produces ATP. Anytime we move to the right on this page, we're going to be doing a catabolic ATP producing process. So now maybe we have enough ATP and we can start storing it. The process that we're going to do to store that glucose that's immediately available is glycogenesis, which we produce glycogen. And then in the liver, if there's any excess acetyl-CoA left over, we can send that through fatty acid synthesis and turn it into fatty acids. So now instead of breaking down molecules, we're building larger molecules, glycogen and fatty acids, these large polymers these larger storage molecules. These are called anabolic processes that they require ATP, which might sound weird. It's like, well, why would we use ATP to store this stuff? Remember that we're doing these processes when we have a plethora of ATP around and we can invest some of it to store anything that's left over. So anything that goes to the right is catabolic, anything that goes to the left is anabolic. Anabolism generally requires ATP, catabolism generally produces it. So all of these processes in this fed state that we've talked about so far are all promoted by insulin, right? And the main thing that I want to point out is that if you focus on glucose, the thing that we started off with, the main, I don't know, the star of the show, I guess, for metabolism, whatever you want to call it, I guess. I don't know. You'll notice that all of these arrows that are promoted by insulin are pointing away from glucose. Like over here at glycogenesis, we're pointing away from glucose. So insulin, it's not necessarily just a hormone that promotes glycolysis or helps us produce ATP. Insulin is simply a hormone that tells our cells to remove glucose from the blood and either turn it into ATP or store it. That's what insulin does. It catalyzes every process that is pointed away from glucose. So if you can identify that going from pyruvate to acetyl-CoA is in the direction away from glucose, you know that that process, the PDC, is promoted by insulin. So from here, now that we have our short-term storage and we're going to start entering that short-term fasting state, we're going to start using gluconeogenesis and glycogenolysis to start producing more glucose. This short-term fasting stage is when we're starting to run out of glucose and we need to start producing more. Then as we start to run out of glycogen and glucose, then we can resort to long-term fasting, which is where we're going to be breaking down fatty acids into acetyl-CoA. That's through that process called beta oxidation. And then if we run out of fatty acids, we can take proteins and then run them through protein catabolism, where glucogenic amino acids are broken down into glucose or something in glycolysis, and ketogenic amino acids are broken down and turned into acetyl-CoA so that they can be sent through the Krebs cycle, all in the goal of producing ATP, which our brain needs to operate. So notice that all of these arrows that are in orange are going to be promoted by the same hormone, glucagon, or again, epinephrine or cortisol, because they're all functionally similar. So everything that's in orange that's going on in these fasted states is promoted by glucagon. Everything that's in blue, which is in the fed state, is promoted by insulin. And kind of like how I talked about how all of the arrows going away from glucose are promoted by insulin, notice that we have a whole bunch of arrows, like this glycogenolysis arrow and this gluconeogenesis arrow, and these glucogenic amino acids arrows that are all pointing towards glucose, which should help you identify that any arrow that points towards glucose in metabolism is going to be promoted by glucagon. If it points away from glucose, it's going to be promoted by insulin. If it points towards it, it's going to be promoted by glucagon. So now we have a hormonal way of connecting every single one of these processes to each other. If we are promoting glycolysis, we're probably going to be promoting glycogenesis at the same time. If we are promoting glycogenolysis, the breakdown of glycogen, we're probably going to be promoting gluconeogenesis at the same time. Once you understand that all of these processes are being promoted by the same hormones, it makes it much easier to kind of follow which hormone promotes which process. Again, to reiterate one last time, if it's an arrow that's going away from glucose, insulin is going to be promoting that process. If it's an arrow towards glucose, that's going to be stimulated by glucagon. So now we're going to start testing our knowledge a little bit here. And the example that we're going to use is diabetics. So diabetics, for some reason, their insulin isn't working. There's two different types. One of the types is an autoimmune disorder that's present pretty much from birth, where your body never produces insulin properly. The other type of diabetes is basically like acquired, where some sort of mutation or something like that has just caused your insulin or insulin receptors to no longer work properly. Long story short, diabetics just don't have working insulin. Something is going wrong with insulin. So because of that, we need to remove all of these arrows in blue on our little map right here. Right, so they're gone. Nice little PowerPoint animation there. So notice for diabetics, if diabetics want to make ATP, there's much less options. They can't go through the normal aerobic respiration route. So the main way that they're going to end up producing ATP is via beta oxidation. Of course, we're going to need those ketogenesis and ketolysis processes for ketone bodies as well. So if diabetics want to be making ATP, their processes just got a lot more complicated because they can't use that normal aerobic respiration like they're supposed to be doing. So ignoring proteins for a second, the main way that diabetics are going to have to use to produce ATP is going to be beta oxidation. This process, beta oxidation, is pretty much their only way to produce ATP down here at the electron transport chain in a very notable and significant way. Non-diabetic humans can do that too, so that doesn't really seem like that's that big of a problem, right? There is a problem with this, and the problem is with this ketogenesis and ketolysis process. So remember how we talked about how these two processes basically allow us to transport acetyl-CoA throughout the body just by turning it into ketone bodies, which can travel through the blood. But ketone bodies are acidic, and our blood does not like to be acidic. So because diabetics end up having to rely on beta oxidation and acetyl-CoA way more than non-diabetic individuals, they're at a much higher risk for ketoacidosis. This is the acidification of the blood, a decrease in pH of the blood, right? So if insulin's not working, we have to take away all of those blue arrows, and our only route to ATP outside of protein catabolism is beta oxidation. Glucose is kind of just left in the blood, and we can't really do anything with it. In fact, the way that they used to diagnose diabetics was by tasting the urine to see if it tasted sweet. Because if it tasted sweet, that's how they knew that that person's body was not doing a good job of removing glucose from the blood, which is done by insulin. Very lovely. I'm sure you guys are glad that you're born in this day and age and not the other one. Unless that's something you want to do. I guess, I don't know. I'm not going to shame anyone for their own life decisions. I don't know. Okay, long story short, diabetics, because they do not have working insulin, they have to resort to producing ATP in a very different way. This leads to ketoacidosis, which is also going to have several other symptoms, most notably for the purpose of the MCAT, hyperventilation, where basically we're going to be breathing off more carbon dioxide. This is going to shift that bicarbonate buffer system in a way that increases blood pH back to normal. Just to kind of show you that, I'll throw up this generic picture of the bicarbonate buffer system up on the slide, where as we start to hyperventilate, the concentration of carbon dioxide is going to decrease. And so if you're thinking through Le Chatelier's principles, if we decrease the stuff on the left, this whole reaction is going to shift to the left. So it's going to shift to the left, and in doing so, it's going to remove hydrogen ions from the blood. Once we remove hydrogen ions, this is going to cause the pH to increase back to those normal levels where our enzymes are going to be happy to be functioning again. So notice how we can use our knowledge of these metabolic hormones to understand the bicarbonate buffer system. We can use it to understand not only diabetics and ketoacidosis, but we can also use it to understand what's going on with the bicarbonate buffer system and respiration as well. So I highly recommend picking one of these two ways of understanding metabolism that isn't just, okay, here's what glycolysis is and here's what the PDC is. Try to connect each of these ideas to each other using either the metabolic states or the hormones, and that's going to make your life so much easier. So in summary, when we're looking at both of these hormones, we're going to start off with insulin. Insulin is released by the beta islet cells of the pancreas. Obviously, that's not something that we've talked about so far. So surprise, surprise. Great. More stuff that you need to memorize. How fun for you. Insulin is also responsible for every single process in the fed state when we have high amounts of glucose in the blood. And so basically, insulin's only goal is to decrease blood glucose. It's going to be catalyzing all of those processes that are pointing away from glucose. We're either going to turn it into ATP through aerobic respiration, or we're going to store it in glycogenesis. Glucagon, on the other hand, is released by the alpha islet cells of the pancreas, and it is responsible for the processes in the fasted states when we have low blood glucose levels. So glucagon is trying to raise that blood glucose to a more normal level. So since its only goal is to raise blood glucose, or acetyl-CoA technically, it's first going to do that through gluconeogenesis and glycogenolysis, then beta oxidation, and then protein catabolism. So hopefully this was just a little bit of a better outlook to actually study metabolism to make it easier. I will be finishing out a few other remaining videos that I have left for the fasted state sometime this month. So be tuned for those if you're looking out for those. I do have, of course, a bunch of other free resources available on my website that you can find at the link in the description. Since my last video, I've released a few new cheat sheets and Anki decks that you can go through and look through to work on various different things. Just highly recommend checking out my website, which is linked in the description for anything else that you might need on the MCAT.